Okay, let's start. The topic for today is algorithms and time complexity. What is an algorithm?
The steps that the program will follow to complete the task.
Yeah, you're talking about the computers here. I would say that in more general it is a precise step-by-step description for how to solve a problem. We can then implement it on a computer, but in general it's a step-by-step description to solve a problem. What is time complexity?
The measurement of the time that the algorithm will take.
Yeah, it's some kind of abstract measurement of time. And we cannot compute to say that this algorithm will take 2.3 seconds, but we can use this way of thinking to compare different algorithms and say that this one is likely to be better in certain cases. An algorithm is an unambiguous description of how to solve a problem, or a precise description of how to solve a problem. The first algorithm we know about is the very famous Euclidean algorithm to find the common greatest divisor for two integers. This one is still in use. People are using it. The name algorithm comes from, do we have any Persian-speaking guy here? And how do you pronounce this? It's difficult even for a Persian guy. What?
Muhammad al-Kharazmi.
Muhammad al-Kharazmi. Yeah. He was a guy who in year 800 wrote down step by step this algorithms for how to do addition, subtraction, multiplication and division. These ones are not in use any longer. Anyway, the name was, as you understand, difficult to pronounce, so even the Latin guys named him simply Algorithmus, and it's from this that we have the name algorithm. But it was a Persian mathematician who is the origin for the name. A very simple problem, wash your hair. How do you wash your hair? I have one description down here. Start by wetting the hair, then rub in shampoo, rinse it away, repeat. And I have it described as an algorithm down here. So it is a precise description. Well, this is not very precise, but it's often presented as in a structured way. The idea is that it should be rather straightforward to translate your algorithm into code. And if it's structured like this, it looks more like code rather than comparing it with this one. Another algorithm, we are asking ourselves, is n a prime number? My basic idea is to check if n can be divided by any of the numbers in the interval 2 to n minus 1. If that is the case, it is not a prime number. So here is my algorithm. Test equals 2. As long as n modulus test is not equal to 0, we are updating this one. It will run from 2 up to n minus, it runs from 2 up to n, actually. And then we are checking if it reaches n, then it is a prime number. We have not found anything that can divide in 2 to n minus 1. If it is not test, then it's not a prime number. Then we have found a number test that can actually divide this one. Does it make sense? This is an algorithm. It's not written in any programming language, and it is a description in different steps for how to solve a problem, and this is the problem in this case. This one should be you should easily be able to translate this one into Java code. Would you be able to translate this into Java code? Yeah, hopefully by now you should. You add a few semicolon and a parenthesis here and there, but basically it is presented in a way that most people who has a bit of knowledge in programming can implement it in some way. What is an algorithm? Well, first of all, it is a step-by-step description of how to solve a problem. That's the general description, but we have certain criteria as well. It should give an unambiguous result. Only one result for each input. It cannot answer yes or no. sometimes yes, sometimes no. It's not the correct answer for an algorithm. And it should give, for every input, it should give one and only one result. Be unambiguously presented is another criteria. Precise formulation that can't be misinterpreted. I usually tell the students it should be rather straightforward to translate the algorithm into a programming language. If it contains all the information you need to implement it without making any design decision, then the description is okay. Terminate after a finite number of steps. No infinite computations. For example, you can compute the value of p in this way. This would not work as an algorithm. It never stops. For every given input, it must be possible to say that it will end after 100,000 iterations or computations. It should have an end. Why do we use algorithms? Why do we write down algorithms for things? What?
For solving the problem.
Yeah, you can do it as a part of your own problem-solving process, but most important is to document solutions and give them away to other people. Communicate. Yeah, so document problem solutions. You have come up with a clever way of solving one problem, you write it down. Then you can reuse it and you can give it to other people. So document them and communicate them. And as we will see, we should also be able to compare them in certain cases using time complexity. But as you said here, we can see it, a sketchy algorithm is a good preparation before you start to do any programming at all. I always bring paper and pen when I do programming, because before I start to do any programming, I take some notes and sketch some ideas. It can be seen as a first step of an algorithm to do that. Another algorithm, sort a deck. How do you sort a deck of cards? Here my algorithm is start by sorting it in colors. It gives you 4 piles. Then for each pile, sort them by rank. And then collect sorted piles to a deck of cards. I would say that this fails in this aspect. It is not unambiguously presented. How do you sort in colors? This one is a good starting point for an algorithm, but we should need a bit more extra details here. You should describe how to sort in colors and how to sort in ranks, I would say. So this is more an outline of a problem solution. It is not the precise step-by-step approach for how to do it. Algorithm description languages. You could describe your solution in ordinary text. You write it an essay on an A4 paper here. Usually it turns out that these are unambiguous. People can interpret them in different ways. They often becomes vague and they are not easy to implement. Another approach, which is basically the opposite, is to use an existing programming language. It is an implementation in itself and it's very strict. If you know, each programming language comes with a certain semantic, so a programming piece of program is exactly an exact solution of the problem. However, it often requires a bit of knowledge about the programming language that you are using, and also it contains a lot of non-relevant details. Semicolon, system out, print line, mathsin, like this. If you are not familiar with Java, you would think, what the hell is this? And why do I need math here in front of this one? So none of them are actually used in practice. We use something that we call pseudocode, a mix of ordinary text and programming language. So it looks like a program, but we remove all syntactic sugar like semicolons and things like this. They are not coupled to any specific programming language, but still they are often easy to understand for a programmer. If you know one language, you take every statement in the pseudocode, you just translate it into your favorite programming language. Not as unambiguous as programming language is one disadvantage, but still rather precise. Sometimes hard to understand use notations. Since I'm a researcher, I read scientific papers once in a while, and some of the researchers are using very strange mathematical symbols, I would say. So it makes it difficult to read. Using mathematics is accepted, but sometimes I wish they could have used plain text to describe it to me, because it would have been simpler. Two examples solving the same problem. The same problem is extremely simple. Can n be divided by 3? My first approach, structured ordinary text. Ask user for an integer, denote this integer n. If n modulus 3 equals 0, inform the user that n is divisible by 3, otherwise do it like this. Or almost like a program. Here I introduce n integer to be tested, I do a computation, and I do a statement here. Both are pseudocode. Which one do you prefer? What? Yeah, most people who have done a bit of programming starts to think that these are too verbose, it's too much text, it just hides the essential part. But anyway, there is no strict rules for what is pseudocode. It should be structured, it should be short and precise, but whether you take this approach or this approach, it's up to you to decide. So it's a mix between programming language and ordinary text, considered to be more precise than ordinary text, but more general than a programming language. They all algorithms use something called primitives, keywords taken from the programming languages. And key, while, for each, everyone is supposed to understand what this means. And also we are using notations from mathematics and logics when needed. So these are the basic building blocks. Whatever representation you are using, they must be able to handle a sequence of instruction, selection, iteration, and simple arithmetics. And if you study more theoretical computer science, you will know that this is enough. You can solve any computer program if you have a program that can handle these 4 things. We are saying that this programming language, whatever it is Turing complete. If you have a computer that can do these 4 things quickly, you can solve any problem, any program, any problem that you can solve using Java or something else. It will be a lot of programming and the code will be ugly looking, but this is enough to solve all the problems. How do you solve a problem? It was an Hungarian, I think, scientist who was thinking and studying people, how do they solve problem? And successfully solving problem. And he said that most of them spends a bit of time trying to understand the problem, then they develop a plan to solve the problem, then they implement the plan, and then they are reflecting over the implementation. As a programmer, we should do it this way. Understand the problem, create an algorithm, a sketch for how to solve it. Implement the algorithm, run the program, and evaluate the result. And maybe go back a few steps and polish it a bit. Are you solving your problems like this? In the first and second assignment, you had a number of problems to solve. Did you take this approach? Yeah, I would actually guess you do. Maybe you are not formalizing by thinking, now I'm creating an algorithm here, but if you are successful, then you read the problem formulation carefully and you start to have an idea about the problem. Then you come up with a plan in some way. And then you have a very good idea about how the problem should be solved. Then you start to implement it and then you run it and test it and polish it a bit. I would say I've been teaching for a number of years and I would say that students sometimes skip the first 2 parts. They know that the result should be some kind of implementation, and they don't understand the problem, and since they don't understand the problem, their idea of how to solving it is rather vague, but they still start to do a bit of programming, and it never works. Before you do any programming, you should have a rather clear idea about what I'm about to do next. You should have some kind of a solution in your head before you start to do any programming. So my recommendation is, as I said earlier on, bring paper and pen. Sketch, come up with an idea for your program, even if it's just a method that is non-trivial, some kind of non-trivial piece of code. Stop and come up with a plan and then implement it later on. There is no point trying to guess what the solution would be like. Anyway, problem solving and how it relates to algorithms. Another problem solving approach is called divide and conquer. What do we mean by that? Well, larger problems are divided into smaller sub-problems, which can in turn be divided into even smaller sub-problems. This is, I would guess that without thinking about it, you do it the same way. We are giving you an exercise here, you divide it in some part in your mind into smaller steps, and then you solve them one at a time. So often it looks like that we have divided our problem into 3 smaller problems, and then we are pointing it out that this particular problem can be solved using these steps. And in the end, you actually end up in something that looks like an algorithm. This looks like an algorithm. You are solving it in this way. Do the dishes. Do you know how to do it? Okay, good. On a high level, rinse away the leftovers, do the dishes and clean up. That's a high level description of how to do the dishes. You take a look at them and you think, well, I was rather vague in this part here. Do the dishes is a rather vague statement. So I try to be a bit more precise, a refinement of the second problem here. I say pour water, add some detergent and wash all the items. I might say that this is still a bit vague. Wash all the items. So I go one step further and I said, okay, repeat until no more items. Take an item, put it into the water, brush it, rinse it, and put it up to dry. Now I start to feel a bit more confident. Once again, I think you do it the same way when you are solving a problem. You divide it into smaller parts, and then you take the smaller parts and you refine it. Maybe you are skipping the last part, you are waiting with this part until the implementation starts. But basically this is how we are thinking when we are solving problems. And if you're formalizing it like I'm doing it here, it often ends up in something that looks like an algorithm. What is an instance of a problem? Yeah?
For example, for the washing the dishes, an example that we all have to wash the dishes, so we have to implement this algorithm in order to solve this particular problem.
Yeah, I would say it is one particular problem out of a more general case of problem. I would say that the instance of this problem would be, how do I wash one plate and one fork? It is a concrete instance of this more general problem. So in most cases we are interested in finding the general solution, but it is always a good idea to start with an instance and try to solve an instance of the problem. Generally, what is the result of adding 2 integers? An instance would be, what is 13 plus 25? If you cannot solve this problem, the likelihood that you will solve this one is minimum. So another example, sort a list of names alphabetically. Well, how should you sort Lisa, Olle, Kalle and Anna? This is what I mean by an instance of the problem. Something concrete which is belongs to a more general set of problems. And of course, my advice and everyone's advice is that you should start with a number of instances. And as I said earlier on, if you can't solve it, the instance problem, it is not likely that you will be able to come up with a general solution to it either. So this is another strategy. Start with a number of instances of it, and then you attack the general problem. How do we recognize a good algorithm? Every algorithm, if it is an algorithm to solve a problem, then it is correct. Otherwise, it's not an algorithm. But we might have more than one algorithm. Which one is the best? Possible criteria: easy to understand and implement, simple, clearly written, well documented. My approach, actually, one good rule or suggestion would be to take the simplest solution first. Try to make it work with a simple solution, and only if you run into time problems or memory problems, you should come up with a more advanced solution. But other criteria apart from simple and well documented should of course be that it is efficient. It can be efficient when it comes to memory or speed, actually. We will from now on talk about time efficiency, how to look at algorithms when it comes to time efficiency, but the other parts here are just as important. My idea is start with the simplest one. And only when you're testing your program, if you have a bottleneck in some performance issue, then you should go for a more complex solution. So the simple is often good enough. We will talk about something called asymptotic analysis. Well, you have all studied mathematics. What is an asymptotic analysis? Or you have studied mathematics, I guess. Then you should recognize this word from your calculus course. How things behave for large, when n goes to infinity, it is usually mathematics. How do they behave for large values? We would like to analyze an algorithm without knowing on which computer they will be executed. We should be able to answer questions like, which of these two algorithms are faster if the input size is big? We cannot say how they behave to sort a list with 3 elements, but we should be able to reason about how do they behave when the list is very large. And you should also be able to answer questions like, how much will the computation time increase if the size of the input is multiplied by 2? If I'm measuring the time to do a sorting for 1,000 elements, I should be able to give an estimate. How long time will it take to sort 2,000 elements in this case? Will it be twice as long? No, it will more likely be 4 times as long, I would say. Anyway, it's a way of reasoning about solutions. So, asymptotic analysis is behavior when input size is big, and what we will do is something called a time complexity estimate. We will give an expression telling how this particular algorithm behaves for large input values. Time complexity. The number, an estimate of required computation time. That's the first. We are estimating something here. It will not be a precise value, like 2.3 seconds. And we must also realize that the time to do a computation often depends on the input data. Find an integer in a list, well, the time depends on the size of the list. If it's short, it goes fast. If it's long, it takes a longer time. Check if n is a prime number. I did it in one of my examples. We were testing all the values. So the larger n we hand in, the longer time it will take. Sort a list, well, it also depends on the list size. Longer list, longer time. Our answer will be something that looks like this. We will say big O of n or big O of n squared. And if we are saying that the algorithm runs in big O of n, it means that the computation time is proportional to n, linear in n. big O of n squared means that the computation one scales or is proportional to n squared. Most sorting algorithms or simple sorting algorithms, they are n squared. That means if you're doubling the input size, it will take 4 times longer to do the sorting. And then we have our big O of 1. This is our statement of saying the time is constant. It doesn't depend on the input size at all. In general, when you see big O of something, it means that the computation time is proportional to this something. I am using big O or just O of. In more mathematical literature, they often use order of as their way of putting it. It's the same thing. We make a few simple basic assumptions. Every simple computation takes time 1. That's a starting point. Plus, minus, whatever. It takes 1 time. Assignment and all things like this. So, print multiplication table. The input parameter n here will determine the time. How will it scale? The time to print the multiplication table, how will it scale with the input data? Well, we are printing a square. So we will, for every n here, we will reach this time n times. Yeah? So this one is big O of n squared. Did it make sense? The larger n, it takes much, much longer time. It grows with proportional to the square. Search x in an array of size n. We have a very simple search method here. We are searching for this value inside this array. We are iterating over the array, and if we find it, we return true, and if we are not finding it, we return false in this case. The time it will take is proportional to the length of this one. We go through all the elements. So this one is big O of n. Does it make sense? So it might look strange if you haven't seen this notation before, but just think of it, how do they scale for large input n? And also, we are always interested in the worst case scenario. You might argue here that it doesn't belong on this one in the case when we find it in the first position. But that's not what we're interested in. We're interested in the worst case scenario. And what is the worst case scenario in this case? We are not finding it. We are not finding it. We have to go through the entire list and we are not finding it. That's the most problematic from a computational time point of view.
Sorry.
Yeah.
How do we estimate by looking on the code? Do we actually tell it by the number of lines of code or by the blocks?
Not at all lines of code. This one has only
one line, but the other one is a block. So
now I would say that take a look at the part of the code that is executed most times. In this case, this particular line here is inside 2 loops, each one running from 0 to n. So this part of the program will be executed n.n times. This is the one that determines the time complexity. If we should have done something in between here, it will be rather painless from a computational point of view. We are just doing it once.
So we mostly focus on iterations?
Yeah, I would say that a simple idea is to try to find a code that is executed most times, and then make an estimate of this code that is executed many times, and then estimate how many times will this one be run. So, and it is often in the inner loops. This is the code that is most executed. Assume that we were able to write down the exact time. The time for handling a problem of size n was 3n. Or the size of handling a problem of size n was this large expression. When it comes to time complexity, we start by saying that constant factors do not matter at all. We skip the 3 here. We're saying that this is proportional to n, so we take this one. Also, in a sum, or if you have many different expressions, we are only interested in the one that grows fastest. So in this case, for large n, this one will be the dominating one. For large n, n raised to the power of 4 will be larger than raised to the power of 3 and all these ones. So if this was the exact measurement of time based on some size, we would say that this one runs in order n raised to the power of 4 only due to this time. So you must use your knowledge in mathematics to recognize which of the different parts that actually will be the contributing one when n goes to infinity. In this case, it will be this one that dominates. In this case, this one looks really ugly. But it turns out that this one grows even faster. When n starts to grow, an exponential growth will actually outrun this one. So if given an n which is big enough, it will be this one who dominates. So we are saying that this one is of type exponential time complexity. Exponential time complexity, it's the worst. You should reconsider your solution if you run into this one. Yeah?
The complexity of the n.
What?
Order n is smaller than order n multiplied by.
But you should always think about n is very large. We don't know how large it is, but it's very large. So it is always when n goes to infinity that we're interested in. In this case, for n being 1000, this one might be the dominating one. But still, we don't care. We want to see how they behave for very large n's.
Okay, I'm asking this example.
Yeah.
Imagine that there is no the second part. It is not exist.
Yeah.
Imagine that.
We have only this one and this one.
Okay, so the big O is n.
The big O is n.
So right now it is mining something.
Minus something.
Okay, so the big O should be smaller.
Yeah. I'm saying that we take the largest term. We don't care about plus and minus. So minus doesn't influence us. The question is, which one is the dominating one? And the dominating one, no matter whether it's plus or minus, is the one that, and by dominating we mean the one that will be the largest one for large input sizes. Time complexity and asymptotic methods, they have they are not very good for everything. They can only give answers about large input sizes, very large in the end, maybe. Which one is fastest, which sorting algorithm is fastest to sort 10 elements? Time complexity doesn't give any hint at all to answer this type of questions. It's just something, a tool to reason about with large input sizes, and the large input sizes are the most problematic cases. Otherwise, we don't have any problem at all. So, it turns out that it almost always ends up in one of these time complexities. Problems we are solving, they are ranging from this one at constant time to the dangerous cases with exponential time complexity. We seldom have something n raised to the power 2/3 or something odd like this. It will be polynomial, logarithmic, or exponential like this. So you don't have to be an expert in elementary function in mathematics. You just need to recognize these and know how to rank them. This one is the one that grows, where is it? Fastest, and this one is the one that doesn't grow at all, and then they are in racing order here. Yeah, let's take a break. 10 minutes. Yeah. Okay. Come on, please be quiet. Before we start, I should answer a few questions that I received here. It's a guy who asks, what about this lecture? Shouldn't it be about time complexity? Yes, it is about time complexity. I guess you asked this question a bit too early. And then it's a question here about the old yesterday we failed in our recording. And he was surprised to see that the slides presented this year fit so well with the lecture recording from last year. It is because I haven't updated my slides there. It's the same lecture this year as it was last year. So we could just have recorded it once 10 years ago and send it to you because it's the same. Time complexity haven't changed anything at all. Okay, let's move on. Sorting and searching. If you take a course in algorithms, the first thing they will talk about is sorting and searching. We do it all the time. We search for things and we are sorting things. I will show a few sorting algorithms and show a few search algorithms. That's the topic. The first sorting algorithm is the simplest one. Maybe you should come up with it yourself if you were asked to sort something. Assume that we have a list of n elements. Find the smallest of the numbers and swap place with the first element. Find the smallest of the n-1 last elements numbers and swap with the second element. Do you understand the idea? I have my list over here. I start by searching the list for the smallest element and I move it to the first position. I'm done with this one. Then I search the remaining part of the list for the smallest element and I move it to the second position. And I do this all the time. So if we have this as our example, find the smallest and swap with position 0. I find the smallest minus 12 and I swap place with position 0 like this. Find the smallest. Now I'm only looking in this element because I already have 12 here. So I'm only looking among this one. Find the smallest and swap with second position. Nothing to be done. The smallest one was already in the second position. Find the smallest among the remaining 4 elements and swap with this one. It looks like this. Simple. Yeah. If you should express this as an algorithm, it could look something like this. Algorithm. Let L be a list with index 1 to n. And then for each I belonging to this interval, say that, okay, this is the position that we are interested in. And then I'm looking through the remaining elements, I plus 1 till the end. I compare them. And immediately when I find an element which is smaller than the current element P, I update P. I just remember the position of the element with the smallest number. And then I swap them over here. And then I move one step forward and I do the same thing, searching for the remaining part of the list. Do you understand my mathematical symbols here? I belong to the range. For every I that belongs to this range, we do something. Yeah. Time complexity. Well, what is your gut feeling?
We got 2 loops.
Yeah.
Which are executed n times.
Yeah.
So it's n times n squared.
N squared, yeah. The simple trick counting the loops works very well here. We are having 2 loops and the part inside here will roughly be executed n squared times. So the time complexity of this one is n squared. Yeah. Yeah. You will see that better, I will discuss this better algorithm later on, so let's skip it. Once you have it as an algorithm, like this, Translating it into code, if you know about Java or any other programming, is rather straightforward. Once again, we have 2 loops here, and I'm just translating it to Java here. The next algorithm is somewhat similar. Once again, we have a list of n elements. Put the second element in the right place among the first 2. Put the third element in the right place among the first 3. Put the fourth element. We start here and we say, okay, I should sort this one. Then I take and swap these 2 because I would like the smallest first. Then I take this one and then I basically move this one to the left until it finds its position where it should stop. Until I find an element which is smaller than this one. What? Yeah, and then I take one at a time. And what I do every time this one is sorted, I take a new element and I start by comparing it with this one. Well, this one is smaller, then I swap them. And then I compare it with this one, smaller, swap, smaller, swap. So.
This is the bubble sorting algorithm.
No, it's slightly different, but it's similar to bubble sort. Bubbles, take it next there. Did you understand this algorithm? Basic idea is assume first p elements are sorted, then focus on the next one, p plus 1, move it to the left until you find a suitable place for it. You are repeating this, swapping it leftwards until you find an element which is smaller than your element, then you stop. Yeah? What is the time complexity? We iterate over all positions. We are taking this one, this one, this one, and sorting them this way. And for each element position, we iterate over all already sorted elements, which are also roughly n. So once again, we have a n squared time complexity here. Which one is the best? Yeah, that's a good idea. These guys are very similar. They have same time complexity. It will not be a major difference if we are measuring the time for these ones. What about an already sorted list? Let's assume that we should sort an already sorted list. Selection sort. Will it be of any help at all that it's already sorted?
Just iterate every element.
Find the smallest one, we search through the whole one, and then we move it here. We go through the entire list, and then we determine that this one is the smallest, so we don't have to do the swapping. But we go through all the elements. And then we take this one and search, and we go through all the elements. We will still do a quadratic time complexity, although it was already sorted. What about insertion sort?
You just don't iterate once, because the next time you have to swap.
Yeah,
It's already
these guys are already sorted. And then I take the next one, and I immediately realize that nothing to do. Take the next one, stop, nothing to do. So actually, if we are handling lists that are already sorted, insertion sort would be slightly better. What about if they were sorted in the wrong order? Any difference?
Yes, in the second algorithm, it will swap in every
Yeah.
step, every.
It will be a lot more swapping in the second algorithm if it was in reverse order. I would always have to swap all the way back to the front and then start and swap. A bit more swapping would it be. But swapping is very fast, so it will not damage it. But they are slightly different. But who cares, I would say, in these cases. They have the same time complexity. For an arbitrary list, they will behave very similar. Who is interested in an algorithm which is very fast to sort already sorted lists? That's we are not that interested in that. Search. We should search for something. Return first position n if found, otherwise minus n. We are searching for this element in this array. This is the simplest approach. We start from the first element, we go through all the elements, and if we found something, we are returning the position. Otherwise, if we cannot find it, we return minus 1. This is a linear time complexity. Yes, did you?
When you go through all the elements, it says O(n).
Yeah. And O(n), it's always O(n). We are always assuming the worst condition. And the worst condition is not to find it. Yeah. Do we have any better algorithms? No. There is no way. If we have an unsorted list that we should search for something, in the end, we must go through all the elements to look for it, if we can find it or not. So there is no better way to do it. I'm just not for an arbitrary list, and then I had to add in a single core machine. You could divide the problem. We are searching for a list. We are searching for an element in a list of size 100. I could, of course, divide it in 4 smaller parts and divide it to 4 processors and reduce the computational time. But in general, we are thinking about 1 core machines. And no one is dividing search into multiple processors. Search is very quick, so it's not a problem. Binary search. We should search for n in a list with this many elements, but the list is sorted in this case. Then the basic idea of binary search. You should be reminded of binary search trees in this case. But the basic idea is look at the middle element. If this is the one that we are looking for, then we are done. If it's smaller, if this one is large, no. If the one we are looking for is smaller than the middle element, then we should repeat the search, but then only in 1/2 of the list. If it is larger than the one, then we are searching in the second half of the list. So the basic idea is that they are all sorted. We take a look at the mid element. Is this the one that we are interested in? No, the one we are interested in is smaller than this one. Well, then we know that it should be in here. And we are repeating this process all the time. We take the middle element, look larger, smaller, and then we decide we should go this way. So this one, we are saying that it halves the problem. We have one problem, and then in just a fixed number of time, we have a problem which is half the size. This one is very fast. We can often reduce, in every step we are reducing the problem size by half. Much faster than linear search. Linear search, that means if you are searching many times, it might be worth the effort to actually start by sorting the element and then do the sorting. What is the time complexity? What? Log, yeah. If it looks like this, if we could reduce the problem with 50% just by doing a few fixed number of steps, then we will end up in a logarithmic time complexity. I have some kind of, I have some kind of motivation here. In order to search a list of size 1, I need time 1. I find it in the first search or not find it. If it's size 2, I might need 2 steps to search it. If it's size 4, I might need 3 steps. If it's size 8, I might need 4 steps. If it's size what? 16, I might need 5 steps. The size is growing much faster than the time here. We can say that size 2 raised to the power of n will take p plus 1 times. So the size grows as 2 raised to the power of n, t. The size, as a function of time, but if we are reversing it, then we get time as a function of size, and then we get this one. The reverse of this function is this function. But the key rule is an algorithm that halves the problem in a fixed number of computations, they always have this time complexity. Implementing it. We are doing the same thing over and over again. We look at the mid element and then decide where to go. This is a perfect example for where you should use recursion. So I have a method here, recursive binary search. We are searching for this element in this array. Then I'm calling my actually recursive method here. I'm saying that the min to start with is 0, the max position is this one, and then I'm calling my recursive method down here. I'm searching for the same elements, but now I'm giving the top index and the smallest index here to search for. If this one, then we haven't found it, then we return false. Otherwise, I find the mid position. Min plus max divided by 2 will give the mid position. I pick out the mid element, mid value. If n equals mid value, done, we have found if n is less than the mid value, we call this method one more time, but now we are searching from min to mid minus 1, the left half of it. If it's larger, we search the right half of it like this. I could have done it without this extra method. I could here have computed the mid element. I could have compared with the mid element, and then I could have copied the left part of it into a smaller array and called this method one more time. But then I have to do all this copying. If you want to make it fast, you should avoid dividing the array into smaller arrays. Then you lose all the benefits of it. So always when you try to do something, they're giving you a data structure. You should not manipulate, you should not change this data structure into smaller ones or something like this. It will cost a lot of time. You should try to manipulate it inside it without changing it. Move elements inside the list or inside the array, not change the array. What about hashing in binary search trees? It was the topic for, what was it, last week. Hash tables. How did they work? What were the conditions under which hash tables worked properly?
Oh, it is not all the hash table, you mean?
Yeah, hash table. Well, assume that the number of buckets is larger than or equal to the number of elements that we have stored, and that the elements are evenly distributed over all buckets. We can then look up an element in 3 steps. We compute a hash value, we identify which bucket to use, and then we traverse a very short list. This is a fixed time, this is a fixed time, and this, if it's evenly distributed and this other conditions holds, this list should be of average length 1 actually. So it's a fixed time, so we are looking up things in fixed time here. It's independent of size. It doesn't matter whether you have 1,000 elements in a hash table or 1 million elements in a hash table. Looking up an element takes the same time. They are quick. What about looking for an element in a binary search tree?
Hash table.
What?
Hash table. I have a question.
Yeah.
In hash table, imagine that all numbers all in a bucket.
Yeah.
I mean, there is a link.
Yeah. Then your implementation is not very good. And then it works like a linked list, and then we have a linear time complexity. So it is crucial to have this time complexity, that these conditions are fulfilled. we have about the same number of buckets as the number of elements, and that the elements are evenly distributed over all buckets. Then we have this time complexity. If we are adding all the elements to just one bucket, we will have a linked list and we will have a linear time complexity.
Or maybe it is all n.
Yeah, ordo n, yeah. Linear ordo n, yeah. So in order for hash string to work as it should and to be as fast as we would like it to be, these two properties are crucial.
So we are assuming that in each bucket we have one number in each bucket.
Yeah, that's the ideal case. 1 or 0. Yeah, another question?
Yes, in order to have in every bucket 1 or 0 element, the key is that the hash function actually distributes the value in the bucket.
Yeah,
So
there are
how can
to identify the bucket where we should store it, there are 2 steps. First, we associate the input with an integer, whatever integer. And then we are, based on this integer, decides in where bucket to jump. So both these must work.
Yes, but the problem is that if the hash function doesn't indeed distribute the values in the bucket,
Yeah,
you have to create a new hash function, or you have it's better to just create more buckets. in order to
no,
change the modulus after the hash function.
no, I would say that better look at your hash this one. Try to come up with some more clever way of generating a larger set of integers here. Yeah. Yeah, so in the ideal case, this is very quick. It is independent of size. It doesn't matter what number of elements we have in our hash table. It's always done in a few steps. Binary search trees. Do you remember how we were working in binary search? We started in the middle, looked at it, and then we decided to go left or right. It is identical to binary search. We take a look at some element and then we throw away one part of it. And then we take a look at another element and throw away another part of it. So it will be the same time complexity logarithmic. In each node, we are halving the problem. Each visited node halves the number of remaining elements, and the number of operations performed in each node is a fixed number. Very similar to binary search logarithmic. I will outline the basic idea of a sorting algorithm which is called merge sort, which is actually faster. It's difficult to understand why it's faster, but it is faster. It's very simple. I have an array up here. I would like to sort it. I divide it in 2 parts. And no sorting is done here. I divide it in 2 halves. I continue to divide it until I have arrays of only size 1. Then I start to merge them, and when I'm merging them, then I sort them. So in this case, I merge this one and this one, then I sort them. Here and here I sort them. And then I merge these 2 and I sort them all the time. I merge this one with this one, and while I'm merging them, I'm sorting them. And then I merge this one and this one into the sorted algorithms. The number of levels here are logarithmic. We are halving the size all the time here. So we have a number of levels is logarithmic. The work in each level is proportional to n. So the total time here is n log n to sort it, compared to the quadratic time complexity we had earlier on. The idea is simple to understand. It is a bit tricky to implement it, since you must avoid creating new lists. You should only work with indices in this time in order to make it run fast. But this one is much faster, and you will notice it if you start to sort more than 1,000 or 1 million elements. Things that can be done that takes a minute with a quadratic, it runs in less than a second using this one. So if you are about to sort many elements, it is worthwhile taking a look at the more advanced algorithms, because they actually make a big difference when it comes to speed. Did you understand the basic idea? Do you have a gut feeling why it's much faster? No, neither do I can say. I can understand the reason in here, but it looks like we're not doing anything at all, but in the end it works very quickly.
When you are merging it, you are just rearranging each two arrays.
We are,
So each time you go after the middle, one time back, down, sorry.
yeah,
You are just taking the 4 elements and rearranging them.
we are rearranging, we are taking these two and merge them into one array, and while we are merging them, we are sorting them.
Yeah, I mean, when you are merging two arrays, those arrays of size 2,
Yeah.
do you also, you just pick the 4 elements and sort them again?
No, when I implement it, I take a look at the first one here and the first one here. I pick the smallest one. I keep track of the first element in both of them. Compare them, pick the smallest, and move that one step left.
You only do 2 comparisons. You compare the first with the first and second with the second.
Yeah,
I mean, alright.
yeah. So, basically, you should do it recursively. You should merge, this is the signature for it. Well, the base case is, if it is of size 1, it's already sorted, we return. Otherwise, divide the array into 2 halves named left and right. Make calls, sort left and sort right. They returned left and right arrays all sorted, and then you merge left and right into one sorted array. You should reuse the arrays, not create new arrays for best performance issue here. Yeah, if you are bored one day, implement it. Or Google on merge sort in Java and you will find hundreds of copies of it. It is a bit tricky. The key here to make it with good performance is that you should reuse this array, not clone it in any way or do anything like this. Then it will be much slower. How about sorting names? We have sorted integers all the time today. I have created a class name and I'm adding a number of names to it here. Jens Nilsson, Jesper Andersson, 4 names, and I add them to this array, and I would like to sort them. How should you do it? Yeah, the compare to is the approach. Have I talked about compare to? Yeah. In order to sort things, whatever things you are using, you must come up with a way of saying that this one is larger than this one. And the traditional way of doing this in Java is to implement the comparable interface. It compares the current element with another element, and it should return an integer, and the size of this integer, positive or negative, tells you whether it's larger than or smaller than. This is the standard way, and Java is prepared for this case. They have sorting algorithms in the library, and if you just implement your own comparable, you can reuse the sorting mechanism in the Java library. And if you want to implement your own sorting algorithm, you should not do it for integers or strings. You should do it for comparable. And then rather than comparing size, you should use the compare to method. Rather than comparing integers A is less than B, you should use the same thing, just using the compare method and ask whether it's larger than or smaller than 0. It is exactly the same, apart from that we are comparing it using the compare to method. Then it will work for everything. It will work for integers, strings, all methods that are implementing the comparable interface. And if you have your own class name and you want to make it sortable, you should implement the comparable interface in some way. Then you can reuse all the sorting mechanisms. You can also use it in the tree set. They also require the comparable interface. But in general, you should know about sorting algorithms, but in practice you don't have to do it yourself. Java comes with sorting algorithms, they come with binary search and all these things. And also most of the classes in Java, string, integer, double, they are all implementing the comparable interface. So if you want to sort strings, you can do it automatically. They will give you an alphabetic order comparison. It would be if you would like to compare strings using some other ordering, you must implement it yourself. Helper class Java util arrays has method for sorting arrays. Java util collection has methods for sorting lists and also doing binary search in them. They are using a modified variant of merge sort, so it runs in n log n time. So it is very difficult for you to come up with something better, I should say so. You should be in deep crisis if you try to beat the Java programmers when it comes to sorting. Yeah, I think that was all for today. Any questions about sorting and searching? Yeah. You should know about the most common approaches to both binary search. You cannot call yourself a computer science student without knowing about binary search. Everyone should know about it. But the time complexity part here is the most important, and it will be relevant in the third assignment. The last part of the third assignment, we have picked out a number of algorithms, and your task is to present the time complexity for these algorithms in your implementation. You could Google time complexity depth first search, and they will tell you the answer right away. But then you must make sure that you have implemented it in the optimal way. So try to base it on your own implementation and try to estimate what is the time complexity in your DFS, in your connected components and things like this. Okay, other questions? As I think I told you, I will be away for 2 weeks now. So if you're mailing me, cannot expect a quick response. You can never expect a quick response, but anyway, it will be even slower this time. Johan posed the question in Moodle. The other teacher that is involved in this course, he will look into it and give, hopefully, good answers. But there is no lecture next week, and I don't think it's any lecture the week after either. So you have plenty of time to handle the graph implementation part and to complete the German school or whatever it was. Okay, see you.